Standard enthalpy of reaction and standard enthalpies of formation. A city of 100,000 people uses approximately 1.0 times 10 to the 11th kilojoules of energy per day. Suppose all of that energy comes from the combustion of liquid octane, C8H18, to form gaseous water and gaseous carbon dioxide. Use standard enthalpies of formation to calculate the standard enthalpy of reaction for the combustion of octane, and then determine how many kilograms of octane would be necessary to provide this amount of energy. We're given the amount of energy, which is 1.0 times 10 to the 11th kilojoules. And we want to find the number of kilograms of octane, C8H18, that is necessary to combust to obtain this amount of energy. There are three parts to our conceptual plan. The first of which is to write a balanced equation for the combustion of octane. Second, we will use heats of formation to calculate the heat of reaction using the relationship that the standard enthalpy of reaction is equal to the sums of the standard enthalpies of formation of products, each multiplied by the coefficient found in the balanced equation, minus the sum of the standard enthalpies of formation of reactants multiplied by the appropriate coefficient from the balanced equation. That information will be used in the third part of our conceptual plan, in which we first convert the number of kilojoules to the number of moles of octane required. So actually this factor is the delta H of reaction for the octane, which will be in kilojoules per mole of octane. Once knowing the moles, we can convert that to grams. Knowing the molar mass of octane, and that is 114.22 grams per mole. Then finally we can convert grams to kilograms, knowing that 1 kilogram is 1,000 grams. So the first step is to write a balanced equation for the combustion of octane. We have C8H18, which is a liquid, and it's going to react with oxygen, O2 gas, in the formation of carbon dioxide, gaseous, plus water, H2O. Water initially is produced as a gas. Eventually it will condense. So to balance this equation, we have 8 carbons on the left, so we need an 8 in front of the carbon dioxide. We have 18 hydrogens in octane, so we need a 9 in front of the water. And then to balance the oxygens, we need a total of 2 times 8 is 16 plus 9 is 25, or we need 25 halves O2. We could multiply this equation by 2, but for convenience we will leave it as it is. So now we move on to the second part of our plan, which is to calculate the enthalpy of reaction of octane using this balanced equation and enthalpies of formation that we will look up in an appendix in a textbook, which is Appendix 2B. So scrolling down, give ourselves some room to work. We're going to utilize the enthalpies of formation that we found in Appendix 2B to calculate the enthalpy of combustion. And so we're going to use the relationship that delta H of reaction is equal to the sums of the delta H's of formation of products multiplied by an appropriate coefficient from the balanced equation. And from that we will subtract the sums of the heats of formation of reactants multiplied by the appropriate coefficient. So from the above equation, we see we need 8 times the standard enthalpy of formation of gaseous CO2, to which we will add 9 times the enthalpy of formation of gaseous H2O, and from that we will subtract one times the enthalpy of formation, these are standard enthalpies of formation, of C8H18 liquid, and also 25 halves times the standard enthalpy of formation of O2 gaseous. So this is equal to 8 times CO2 is negative 393.5. That value is in kilojoules per mole, but we're multiplying by 8 moles of CO2. So this is a value in kilojoules. To this we will add 9 times the enthalpy of formation of the gaseous water, minus 241.8. which gives us an answer in kilojoules, minus just 1 times the heat of formation of the liquid octane, minus 250.1 kilojoules. And just for completeness, it'll be minus 25 halves times the heat of formation of oxygen, which is 0.0 kilojoules. So, putting this all together gives us an enthalpy of a reaction of octane of negative 5,074.1 kilojoules, and that's for every mole of octane. We're now ready to proceed to step 3. Our city uses 1.0 times 10 to the 11th kilojoules of energy, so this is a negative number. So starting with negative 1.0 times 10 to the 11th kilojoules, and we know that 1 mole of octane reacts to give us 5,074.1 kilojoules. So the kilojoules cancel, leaving us with moles of octane, which we'll now convert to grams using the molar mass of octane, which is 114.22 grams per mole. So the moles of octane cancel, leaving us with grams of octane, which will now convert to kilograms, knowing that 1 kilogram is equivalent to 1,000 grams. So the grams cancel, and we have an answer of 2.3 times 10 to the 6th kilograms of octane. Checking our answer, the units of the answer, kilograms of octane, are correct. The answer is positive, as it should be for mass. The magnitude is fairly large, but it is expected to be so because this amount of octane is supposed to provide the energy for an entire city.